All right, so what we need to remember from when I just taught what polar is how to get x and y. So we're just going to write up here at the top how to get x and y. Does anyone remember? If not, I'm obviously going to tell you, but it's been like 2 classes since we went over this, but do you remember? Oh, good. R cosine theta and y is r sine theta. Beautiful. So do you remember when we did the derivatives for parametric where it was dy dt over dx dt? It's like the same thing here. Okay, so when we find this derivative, it's going to be dy d theta over dx d theta. It's like the same exact idea. So it's not really any different. And also same thing when we do a second derivative. Do you remember how we did the derivative of what we just got, but then we also did what? Over dx d theta again. And it's like your acceleration would be like feet per second per second. All right, so you're going to do the derivative of what you just had. Oh, I'm sorry, that should be a theta. It's dy dx, but they're in terms of theta, so it's derivative with respect to theta. And then you divide by dx d theta again. So again, think of it like an acceleration. It's like a feet per second per second. You just divide by that again. And this information is the same too. Think back to parametric. How did we get a horizontal tangent line? What did we set equal to 0? Yeah, it was dy dt, right? But this time it's just going to be dy d theta. Like it's going to be with respect to theta. You're going to set that equal to 0. Vertical is dx d theta. You have to be careful with those though, and always kind of check what the graph looks like. And you'll see why when we get to that. So we're just going to practice finding some derivatives. These are very heavy on the product rule. So let's just real quick verbally review product rule. Product rule is the first thing. Derivative of the second plus second times derivative of whatever order you want to do that in. I do first derivative of the second plus second derivative of the first. It doesn't really matter. Whatever order it's in, it will mean the same thing. Okay. But this is very heavy on the product rule. Okay. So first here, let's find x and y. So x equals r cosine theta. So that would be cosine times cosine, which would be cosine squared. And then y would be r sine theta. And r is cosine, so it would just be cosine times sine. Are we together to there? R cosine theta and r sine theta. So when we go to find our derivative, and again, I know it's weird. It's called dy dx, but then it's all like in terms of thetas. You're going to do the derivative for y, and then put a big old fraction bar, and then the derivative for x. All right, so derivative of y. And this is why it's very heavy on the product rules, because you usually have 2 things multiplied together. So it would be the first times derivative of the second. So derivative of sine is cosine, plus the second times derivative of the first. Derivative of cosine is negative sine. And then underneath, we're going to do dx d theta, so derivative for cosine squared. That one's actually going to be a chain rule. What would that derivative be? Good. So you bring the 2 down, it drops to a 1. I don't usually put the 1. And then you multiply on the derivative of cosine, which is negative sine. I usually do nothing to these. There is really not much you can do to that to make it look nicer. The only thing you could do is what would cosine times cosine be? Yeah, you could do cosine squared, and then this would be minus sine squared. But like, what are we trying to do here? Like, that's it. Now, I am going to do something in the calculator real quick because I saw one that was on the homework like this. So I'm going to show you how to do this in the calculator. If you get asked for a second derivative at a particular value. So I'm going to ask for the second derivative at 2, like such that theta equals 2, because this is going to be a little bit of button pushing, and I just want to show you how to do that. Oh, and we just reviewed this on the AP problem we went over. How do we do a derivative in the calculator? All right, everybody hit math 8. I know it's theta, but just hit d dx. We want to do the derivative of what we just found. So I know this is going to be really obnoxious, but that's what you're going to type. Okay, hit alpha y equals to get the fraction bar, and then just go and type it all in. Cosine x, cosine x. I'm going to do minus sine x, like just put a subtraction in there. And then on the bottom, I'm going to put the negative out front. It'll be -2 cosine x, sine x. And just be careful with all the parentheses, because every time you hit sine or cosine, it's going to start a parenthesis. So then you have to end it. But I'm just going to leave that up there for a minute. Just make sure that yours looks like mine. It should look pretty much exactly like what's on your paper. And then at the end, you're going to put such that 2. I just picked a random number. Here, let's try one. All right, moment of truth. What do we end up with? Good. You guys are good with the calculator. All right. So it'll be 3.491. Oh. So we got 3.491. But we're not done yet, because you have to divide that by what? Like we did the derivative of what we just had, but then you have to divide by. Yeah, you have to do this one again. But what are we plugging in for theta? 2. So it'll be over -2 cosine of 2 sine of 2. And I'm sorry, I went right to the edge of the paper there. So you're doing this denominator again. We're just plugging in 2. Now, so that we don't have to store this, here, wake up. I'm just going to hit divided by. And as long as you put parentheses around this, it'll divide by the whole thing. So parenthesis, -2 cosine of 2 sine of 2. And then that would be your answer. So we did a math 8. That's the derivative of what we just found. But then you have to divide by dx d theta again. And it was dx d theta at 2 specifically. What did we get? Wait, I don't think mine's right. What happened? Oh, I didn't put the 2. Hold on. Let me fix it.
I got 4.6.
You know what? I'm gonna have to clear and go back. Okay, so I have that divided by parenthesis. I forgot the 2. See, you know what? This is exactly why I don't like the calculator stuff. If you hit one button wrong, it's wrong. I forgot that 2 and my answer was wrong. There we go. 4.614. Be super, super careful with your calculator. I typed it all correctly, except I forgot to put that 2 in. And my answer is wrong. So anyway, the point is, do the derivative of what you just had and then divide by dx d theta again. Let's try another one. First, you find x and y. X is going to be r cosine theta. So that would be tangent times cosine. And then what would y be? Yep, tangent times sine. Do you see why it's going to be really heavy on the product rule? Like you end up with 2 things multiplied together. So it's going to end up being heavy on the product rule. All right, so we're going to do dy d theta first. So it will be first, just tangent, derivative of sine, which is cosine, plus sine theta, and then derivative of tangent. Derivative of tangent. Good. And then in the denominator, we're going to do derivative for x. So it will be tangent times derivative of cosine is negative sine plus cosine times derivative of tangent, which again, secant squared. I would do nothing to that. There's nothing that's going to make that any more pleasant. Just leave it alone. So as long as you know the product rule, you're basically going to be okay. So now I'm going to ask you about some horizontal and vertical tangent lines. Find the coordinates of the horizontal and vertical tangent lines of r equals sine theta. We're going to go from 0 to pi. I don't want to include pi though. Can we change that to just a less than and not a less than equal to? I apologize. I don't want to include pi. We'll leave out pi. Now it says write the answer in both rectangular and polar. That's why we kind of went over how to convert those and graph them so we know what that's going to look like, because sometimes you might get asked for both. Okay. So let's do horizontal first. Let's find y. What would y be for this? Have a good weekend. So for this equation, sine squared, it would be sine times sine, so sine squared. So dy d theta. Derivative of sine squared. Good. And we're going to set that equal to 0. Horizontal tangent line. Now 2 equals 0 doesn't make any sense. You can think about dividing the 2 over. 0 divided by anything is going to be 0. You're going to set each of these equal to 0. So we get sine equals 0 and cosine equals 0. It's like when you factor something and you set both of the factors equal to 0. Now remember, we're only going from 0 to pi, and I'm not including the pi. So think about your unit circle. We filled one out last time we actually did class. Where is sine going to be 0 from 0 to pi? At 0 pi, good. And I like to put pi on there because like it helps you remember it's nothing pi instead of just a 0. All right, and then where is cosine going to be? Cosine is the x value. Good, just pi over 2. So let's do the polar coordinates first. It says we want them in both rectangular and polar, but we have these angles. So let's do polar first. It's r comma theta. So we're going to have something comma 0 pi and something comma pi over 2. It should really be theta comma r. But it's r comma theta. So if you plug 0 back into the original equation, I'm looking back up here. This is our r equals equation. If you plug in 0, what do you get? 0. Cool. And if you plug in pi over 2, what do you get? 1. So that's polar. Now we're going to convert them to rectangular. Now these are going to be on the quadrants. So I think it's honestly easier just to like visualize what they would look like. Where would this one be? If your r is 0, yeah, it really doesn't even matter how far you rotated, because if you didn't go anywhere, like you're at the origin, like it's just going to be 0, 0. It could be 0 comma a billion pi. It wouldn't matter. If you go nothing, you're at the origin. And then let's think about this one. If you rotate to pi over 2, that's going to be here. And if you go 1 in that direction, 0, 1. So those are our polar coordinates and our rectangular coordinates. They asked for both, so we did both. So that was horizontal. Now we're going to do vertical tangent lines. So now we need x. We're basically going to repeat the problem except do x. So what would x equal? Good. Sine, cosine. It's r cosine. R is sine. So sine, cosine. So now we're going to do dx d theta. And it's going to be a product rule. So it'll be first times derivative of the second, which is negative sine, plus the second times derivative of the first, which is cosine, and we're setting it equal to 0. So this would be negative sine squared. Coming with me on that? Because if we think about it, we won't have to write as much. That's negative sine squared. This would be cosine squared. I'm going to add this to the other side. What will that give us? Good. So I just took this and added it to the other side. Then you would want to square root, which does give you cosine equals sine, but when you square root, what do you also have to put? So it's plus and minus cosine equals plus and minus sine. So here's what we're looking for. Think about your unit circle from 0 to pi. So like just that half rotation. You want angles where sine and cosine are equal, but it doesn't matter what sign they are, like positive and negative. I know it's weird because I'm saying sine and then I have sine of theta, but you want places where these are equal, but positives and negatives don't matter. Good. Pi over 4 and 3 pi over 4. Because that's where you get the square root of 2 over 2. Okay, good. Heads nodded. So they asked for them in polar and rectangular. So let's do the polar first. It's going to be something comma pi over 4 and something comma 3 pi over 4. What's that? So we wanted places where sine and cosine are equal, like these are equal to each other, but the positive and negative doesn't matter. So that would happen at pi over 4. They're actually both square root of 2 over 2. And then in the second quadrant, you have negative square root of 2 and positive square root of 2 over 2. So we're going to plug these back into the very original equation. So if you plug in pi over 4, coming with me here. Square root of 2 over 2. And if you plug in 3 pi over 4, sine would still be like positive in the second quadrant. Square root of 2 over 2. And then we're going to do rectangular. So we already wrote out what x and y equal. They're right here off to the side. So it has to be x comma y. So let's do x first. Sine of pi over 4 gives us square root of 2 over 2. Cosine of pi over 4 gives us square root of 2 over 2. If you multiply those together, what are you going to get? The numerators will give you 2, right? And then denominators are 4. So 2 over 4 would be a half. And if you plug pi over 4 in up here for y, isn't it going to be the same thing? The square root of 2 over 2 squared, which would be a half. So a half comma a half. And then we're going to do the same thing with this one. It's going to be the same thing, but with a negative in it, right? If you plug in 3 pi over 4 over here for x, the only difference is cosine for 3 pi over 4 is negative. So it will give you negative a half. And then if you plug in up here for y, it'll be positive a half. I want you to see it visually because that helps. On your calculator, go to mode. We need to be in radian mode, but how do I turn it into polar mode? Where do I need to go? Like, do you remember where this is? Like it says polar, but do you see it right there? Like we had function, this should say rectangular, but function parametric polar. Change it to polar. Go to y equals, only it won't say y equals now, it'll say r equals. And we're going to put in sine theta. And then hit window. We wanted our thetas to go from 0 to where? 0 to pi. So change that 0 to pi. Leave the theta step around 0.1. That's fine. Let me see. I think if we make both of these -5 to 5 will be good. Just make your x minimums and make all the minimums -5 and the maximums +5. I think that'll be good. And then hit graph. Here, I actually could have made it smaller than that. But did you get a little circle? Yeah, you know what? Actually, let me zoom in on mine a little bit. Let me make it -2 to 2 so I can point to this for you. There we go. Okay, look. Do you see how there would be a horizontal tangent line here and here? And then vertical would be, do you see how this is 1/2 comma 1/2? And then another vertical one at -1/2 comma 1/2. Okay, just want you to see it because I think the visual helps that like sink in. All right, so 4 says, find the coordinates of the vertical tangent lines for this equation. We're going from 0 to 2 pi, so whole way around. Now it just says put them in polar form, so we're not going to have to convert them to rectangular, so that's fine. Now, here's what I would do first. Do you see how there's a 2 sitting out front for this? I would go ahead and distribute that, so this can all be like one cohesive thing instead of having that 2 sitting out front there. So go ahead and distribute that. It'll be r equals 2 minus 2 cosine theta. It's the same thing we did on the other side of the paper. It's just this one's a little bit more of a complicated equation, so it's going to be a little bit more complicated problem. So do we want dx d theta or do we want dy d theta for this one? Good, because it says vertical. So first we have to find x, and then we can do dx d theta. So x is going to be r cosine theta. So this is r, and then times cosine theta. All right, so now we're going to do the derivative. And again, it's a product rule. These are mostly going to be product rules. This entire thing is the first function. This entire thing is the second function. All right, so it'll be first times derivative of the second plus second times derivative of the first. Now, 2, what's going to happen with that? Like just 2. Yeah, that'll go away. So we've got negative 2 cosine. What would that derivative be? Good, it'll be positive 2 sine theta. And what do we want to do with this entire thing? Set it equal to 0. So now we have a whole bunch of algebra to get through, and it's going to look like complicated algebra because of all the sines and cosines, but like you guys are in BC calculus, and I believe you'll be okay. First thing we're going to do is take this negative sine theta and distribute it through there. So that will give us negative 2 sine theta plus, because these negatives are going to cancel, 2 sine theta cosine theta. Plus, and then multiplying these together, I'm just going to like put this part out front. And I like when sine goes before cosine. It doesn't technically matter, but just so it looks the same as this one. Plus 2 sine theta cosine theta. So look through that. What would you do next? Or what do you notice? Or like, what do you see that could be kind of like done there? Well, you have 2 of them here, and then you have another 2 of them here. So they don't cancel, but you like combine them. You'd have 4 of them. So negative 2 sine of theta plus 4 sine theta cosine theta equals 0. Okay, that shortened it. That was good. Then what? More algebra. I know that's filled with sines and cosines, but we haven't actually done any trig yet. This is like all algebra that we're kind of distributing there. What do you notice they both have got? So we could factor out sine. What else could we factor out? 2. Can I take a negative 2? Okay, so we're going to take negative 2 sine theta out as GCF, greatest common factor. What would be left? Good, perfect. So we're going to set this equal to 0, and we're going to set this equal to 0. We've got it split into 2 things. Negative 2 equals 0 is not going to give us anything. So the first one, sine theta equals 0. That'll just give us 0 pi. Oh, actually, and we're going further this time, aren't we? Aren't we going the whole way around? Oh, yeah, we're going the whole way around. So it'll be 0 pi and... we're not going to include the 2 pi, but we'll get 1 pi. So 0 pi and 1 pi. And then if we set this equal to 0, I'm going to talk you through a little bit of the algebra so we don't have to write as much. You would subtract the 1, so we'd have a negative 1, and then divide by, good, so it would be cosine equals 1/2. I will draw us a triangle. I know a lot of people just like to visualize their unit circle, but there are 2 places on your unit circle where cosine is going to be a positive 1/2. One of them is going to be in the first quadrant. If cosine is 1/2, that means the other side is good. And so what's this angle? Good. So theta is pi over 3. What quadrant is the other one going to be in? I need another place where my x value is a half. 4, good. I know, I'm asking you to remember like all of pre-calc, which was a while ago. So what would that angle be? If you go the whole way around, well, not the whole way, almost the whole way around. So here's the thing with the negative angles, because you're not wrong. It could be negative pi over 3. It comes back to this though, and the rotation needs to be between 0 and 2 pi. So we're being forced to go the whole way around like this. Good, 5 pi over 3. So how many answers did we get? Looks like 4, okay. Let's go and put them in polar form. So it's going to be something comma 0 pi, something comma 1 pi, something comma 5 pi over 3. Oh, let me do pi over 3 next. And then something comma 5 pi over 3. And you're going to take them and plug them back into the original equation. I know, super fun, right? So let's plug in 0. Cosine of 0 is not 0. Cosine of 0 would be 1. But then 1 minus 1 would be 0 times 2 would be 0. All right, then we're going to do pi. Cosine of pi would be negative 1. So you'd have 1 minus negative 1. 2 times 2, 4. Cosine of pi over 3 would be a half. That's like the picture we drew here. 1 minus a half be a half times 2 is 1. And then you actually get the same thing for that one. Look at it on the calculator. You always need to do this because sometimes weird stuff happens, and that's going to be the case here. Hit y equals, but it won't say y equals, it'll say r equals, and we're going to type in this original equation. And we want our theta to go 0 to 2 pi. And let me see, I'm going to change this back to negative 5 to 5. I think that should be okay. And then hit graph. Oh yeah, that's good. Do you get a little like heart thing? Okay, so let's find where all these are. Did we find vertical tangent lines? Vertical. Okay, look. One of them's right here. Do you see how this would be a vertical tangent line? I can't draw on the calculator screen though. Which one is this? Which one of our answers is this one? Yeah, this one. You would have one right here and one right here. Do you see those two? Again, I can't draw on the calculator screen. So are you seeing this? Just what I'm pointing to? All right, which two would those be? Yeah, those would be these. Now this one would be right there. You actually have to dismiss that answer. We don't get a vertical tangent line there because what is there on the graph instead? Sharp edge. What do we call this? I'm glad you said sharp edge because that covers everything, but do you remember what those are called? Like the thing that does this? Oh, cusp. Good. I was wondering, I'm starting to wonder if you'd ever learned that, but yeah, a cusp. So you have to get rid of that. You should always look at the graph. Weird stuff happens with these. So we actually only got 3 answers. And this last one, we're not going to do a whole lot with this, but it's a theorem that's true. Okay, so I'm just going to show it to you. If your equation goes through the pole, which is the origin, and your derivative's not 0, then you get a tangent line there, is what this is saying. So if you go through the pole and your derivative's not 0, you'll get a tangent line. Number 7, well, I guess it wasn't yesterday, last class, whenever that was. I'm just going to draw it real quick. I just like sketched it here. It was the one that looked like the 3-leaf clover. Do you remember this? I think it was the very first one we did. Okay, don't judge my art skills. But do you see how we go through the pole several times there? As long as your derivative's not 0, you get tangent lines. So we had one for pi over 6. Do you see that there? We had one for pi over 2, and then we had one for 5 pi over 6. That didn't quite go through the origin, but do you see that there, how those are all our tangent lines? So if you go through the pole and the derivative's not 0, you're going to get a tangent line. Do you remember the ones that we did that had like all those petals on? That means all of those would be tangent lines. It's just true.